Hi, Leonard Vance here for American Checker, and this time we're going to talk about arm design. What I've got here is the original throwing arm for the very first Merlin that was ever built. And I'm going to use it to illustrate the basic principle of trebuchets involving the throw. So we're going to have the throwing arm, which is pivoted about this point right here. We got a projectile, which in this case is set up on the back, and the arm starts off pretty much like this. So there are three phases that follow. One is that the counterweight starts to drop, and regardless of the type of trebuchet, what happens there is you're converting some of the potential energy into kinetic energy on the counterweight. So during this time period, the arm moves relatively slowly, and not much energy is happening, and not much is changing on the geometry between the projectile and the arm. In the second phase, the counterweight is getting close to the bottom of its throw. And so now the energy is starting to get pulled into the arm. It's going to move the arm around very quickly. Now, the projectile hasn't started to deploy very much, but very quickly it's going to end up into the third phase. In the third phase, the arm is going at very high speed, but now you have a harvesting motion that's going on where the sling comes around and it slows down the arm, hopefully to the point where the arm is just about exactly stopped before the projectile comes off and it goes off and flies. So three phases to worry about, and the king of making all of this work is the harvest portion of the activity, and the harvest portion of the activity is only successful in as far as you can make the inertia of the arm light enough so that when you swing the projectile around, it actually stops the arm. This year we started out with the same basic steel lattice that we had been successful with for previous years. So this is basically a tetrahedron design. It's got two arms in compression in the back, one in tension in the front, a bunch of girders holding them in place in between. And when you work that out, then we came to an interesting realization. One is that we're building something that's 30 feet long, not 12 feet long like we've done in the past. And so this is a very different beast, and it's a lot heavier and a lot bigger and a lot more expensive. So when we lay the whole thing out, it becomes a very difficult thing to actually build. Not the least of which because you're dropping that huge counterweight down from 30 feet tall until it gets down to about 10 feet down. And then it's going to push all of that weight into the motion of the arm very quickly. And it turns out that the forces that are on that arm are driven by the weight of the arm itself and practically not at all by the pumpkin. So this was a realization that was a bit unpleasant to discover because we realized that our biggest problem is just figuring out how to make the arm not bend into a pretzel while we're throwing. The weight of the pumpkin is almost not important on top of all this. It doesn't add very much to the stress. So we went off and did some modifications to the arm. It turns out that the stresses are very high at the base of the arm, and they're lower at the tip of the arm, and that was what you would expect. But when you take a look at the inertial contributions, and what is inertia? Inertia is not the weight of the device, it is the amount of force that it takes to rotate the arm. So the interesting part is that even if you take into account that the forces on the arm go down as they go out, if you size all those elements so that they get lighter as they go out, and as light as they can be, they still contribute far more inertia even though they're lighter out at the tip than they did at the base. And so that was to the point where the arm really couldn't be built. It wasn't just a question of how heavy it could be, it's a question of whether it could be built at all, because you get this runaway effect where increasing the inertia increases the forces, which increases the inertia more to deal with the forces, and so forth and so on. And so we ended up with a problematic design. Basically, the basic tripod design, it doesn't work. So we went to a modification. So here we've spread the tension and the compression part apart from each other out towards the tip. And even though that doesn't change what happens down at the base, out at the tip, the amount of forces are much less than they were in the previous design. And so now this particular design is capable of getting down to within the inertias that we're capable of dealing with. But only just. I mean, if you take a look at all of the things that you're going to have to do to make sure that you've got connectors and the welds and all the other pieces you might have to do to buttress it up so that it works, that's going to be problematic. And that led us, not to mention the fact that it's got 84 structural elements in it, that it's a complex thing to build. And if it bends, well, we're kind of done. So we decided to take a look at another direction. Instead of going with steel, we thought, let's try aluminum. Well, if your yield strength on steel is about 100 KSI, and depending upon the strength of the steel and its cost, on aluminum it's more like 40, so it's lower but not hugely lower, and it's a little bit less than 1/3 of the weight. And for the same amount of weight, it takes up a considerable amount of volume, which means that, okay, the air friction is a little bit higher, but the buckling strength is also much higher. So there's all those real good things that happen. The other thing is, of course, if you've noticed with the structure that we had already had, is that half the elements are under compression, but half the elements are under tension. The neat thing about that is that you don't have to build something which is bulky to deal with tension. And so we came up with the concept of running stay wires, just like you would for a sailboat mast here. And instead of using steel, we could use AmSteel Blue, which is about 1/8 of the weight for the same strength as steel. So it makes a huge difference. When you put the whole thing together, it gets lighter, which means that the forces are lower, which means that the inertia goes down even further, and you get this compounding effect where you end up with about half of the inertia that we had for the original steel piece. And the number of elements has gone down. Now you have 2 pieces of aluminum, just 2 pipes, and you've got a couple, 1, 2, 3 ropes that you've got to rig. And that's it. So we've gone down from 84 pieces down to 4, and the inertia's gone down by a factor of 2. And the cost is, well, if anything, less with the aluminum than it is with the steel. So easy trade study, and we're done. Of course, we've got to do things like, we've got to decelerate the arm instead of just accelerating it. And so we've got to put stays in the back and in the front, but they're pretty small. So we've gone ahead and progressed in that direction. This week, the crew is up starting to cut the cam that fits into all of this and finishing up the frame with the hydraulics on the trailer. So this is where we are right now. You can see the 30-foot tall frame connected to the trailer, and they've got at least partially up to vertical. They're working on the later part of that this week. So pretty soon here, we're going to be building that arm and starting moving some of the pieces, and I'm looking forward to telling you all about that. We'll talk to you next time. This is Leonard Vance from American Checker, and we'll see you later.
Well, the first days are the hardest days, don't you worry.